Well, hello everybody, and welcome to a video on how to boil water. Now, you fully understand that you already know how to boil water. So the idea is, what I'd like to do is show you some details about how to link what you already know how to do, boil water, with what you're doing in thermodynamics class. So we're going to get started by, we're going to boil water in this clear whistling teapot. Let's get a little water in here. Okay, I have filled it up to the minimum amount, 250 milliliters, and I've got this handy thermocouple and handheld device here, and we're going to measure the temperature of the water in our pot. And see if I can show it to you. Okay, it says 18.7. Let's call that 19 so we can do some specific math here. So, okay, so we've got that. And now, let's see, next thing is I'm going to put this on the stove, and then we're going to go look at some PowerPoint slides before we go live again. Okay, here we go. Give me a second to get resituated here. Okay, that's looking pretty good. I need to put my thermocouple back in here because we're going to monitor the temperature as we start boiling. So I'm putting my thermocouple, I built a little jig here so that my thermocouple fits fairly well. Okay, and let me come up here to show, okay. All right, and then I'm going to set up my thermometer so that you can see. Whoops, we're getting there, just bear with me. I think that's going to work. So you see what I have is, I don't know if you can see. Yeah, there we go. We can see pretty well. Let me move my pot a little bit. And so do you see the thermocouple down in the water? Okay, it's well immersed in the water and you can see the temperature. And now I'm going to share my screen. I'm going to share my screen so we can look at some slides before we get started. And just bear with me a second. Okay, we're going to talk about boiling water. And the first thing I'd like to do is, today is my mom's birthday, February 9th. So she was born in 1919, and a couple of pictures. The left-hand picture is my mom and dad on their wedding day in 1943. On the right is our last family photo that was taken around 2000 or 2001. So really owe a great deal to my parents and want to wish my mom a happy 105th birthday, although she did pass away in 2008. Now, another reason I'm bringing my mom up is because she introduced me to the idea of boiling water. So even as a child, she would explain to me the idea of water coming out of the tap and then boiling it, and things that, of course, we could do in the kitchen with boiling water. So happy birthday to my mom. Okay, so here's a picture of boiling water on the stove. And the pressure, our pressure here in Daleville is right at 100 kPa absolute pressure. Can you predict the temperature of this boiling water off the top of your head? I hope so. I hope that you've sort of learned through practical experience even before you got into this class, that the temperature of this boiling water is right around 100 degrees C. Okay, and so we're gonna light this off here in just a minute and see what happens as we increase our temperature from, let's call it, it says 18.8 right now. Let's call it 19. My slide says, could you predict the temperature of this tap water? I think I've just disclosed it to you right here, but within a range, what would you expect tap water temperature to be no matter where you are? I would expect the temperature of tap water to be somewhere between 15 and 25 degrees C. So we're right there in that range. So our objective for this video is to basically turn this tap water into boiling water, is to boil this water and link what we observe to our thermodynamics class. So let's plan how we might boil water. Well, let's start with a sketch. And so I've drawn a pressure-specific volume diagram. I've drawn in our vapor dome, and I've labeled our pressure at 100 kPa. So we need to label this line of constant temperature. Okay, this line of constant temperature that corresponds to the boiling point at 100 kPa. How would we do that? Well, we will go to the temperature table. We'll go to the pressure table, and we'll look down the left column at 1 bar, which is 100 kPa, and we'll simply write down the boiling point temperature is 99.63, or in other words, right at 100 degrees C. So there's our label of our isotherm. 99.63 degrees C is the boiling point temperature at our kitchen pressure of 100 kPa. Let's see where we're starting at. Where are we starting at? What's the phase of water in this tea kettle? Okay. We just measured it to be 19. We're going to say it's 19 degrees C. Okay. Well, so I've drawn in another isotherm below 99.63. So I've drawn in another isotherm. And so where's our state? Our state must be on the intersection of this temperature line at 19C with our pressure horizontal line of 100 kPa. So there is our initial phase in our tea kettle, compressed liquid, also known as tap water, also known as subcooled liquid. In other words, liquid that's cooled below the boiling point, 19 degrees C. What we're going to do is we're going to fire it up. Okay, we're going to fire this up, and we're going to heat the water up until it comes to the boiling point of 99.63. So we're adding heat. We'll call it Q dot in. So we're adding heat at some rate, so many kilowatts. Okay. So the water temperature is going to increase from 19 up to the boiling point of about 100 degrees C. We're going to continue to add heat. So we're going to watch the process. We're going to continue to add heat and observe boiling water, and we're going to watch what happens with the temperature. And it's my hope that we're going to observe that the temperature stays constant through the boiling process. And finally, what we're going to do, I need to make a mention of how would we, if this were a homework problem, how would we model our process? And so it's a little subtle, but I need to address this. Here's our glass kettle. Here's our glass kettle that we're starting with. Do you see that this is water? But what's this up in here right now? This stuff up in here is air, isn't it? We could call this a closed system of water down below here. We've got this air sitting on top. Now, once we're going to heat and heat and heat this until the water starts boiling. Now, I hope you know what's going to happen. As the water starts boiling, saturated vapor is going to be created and the air is going to be displaced. There's a hole. This is a whistling tea kettle. And there's a hole in the top here where steam can escape. So the first thing that we'll do is that air will be removed from the tea kettle. Air will be essentially pushed out of the tea kettle, okay? And what's going to replace the air is saturated vapor at its boiling, okay? And so recognize we start out with a closed system, but as soon as the boiling process begins, you see, notice here on the slide, you see that we've got steam escaping from our system. And so here, as we're boiling water in this real world, we've got an open system where our mass of our tea kettle contents is slowly decreasing because we've got steam escaping from the top. It's my hope that you're going to be able to hear the tea kettle whistling as we go along. Okay, so let's go live. Okay, so I'm going to move over. Okay, here I am. Okay, I'm going to turn on the heat. Okay, so we're heating now, and in just a second, there we go. So the cloud created from the exhaust gas of our gas stove is starting to clear because the tea kettle's starting to heat up. Now, let's see. Let's keep an eye on our temperature here. So, wow, we've got a pretty good amount of heat. So let's look at what's going on. Can you visualize that we're adding heat to our closed system at a certain rate? Okay, we've got this is natural gas combustion. So we could make a little calculation if we knew the flow rate of the fuel. We could calculate how many kilowatts or kilojoules per second of energy we're adding to our system here. Okay, wow, let's look. We've already got 29 degrees C. So we're raising the heat, the temperature of the compressed liquid. What this is called is sensible heating. We're not boiling yet. We're not at the boiling point. Okay. So it's called sensible heating in engineering jargon, where we're simply raising the temperature of our water. Let me set my timer on the stove for, let's say, 10 minutes. Okay, so I've set, there's my timer. So we're going to give ourselves 10 minutes and maybe more. As we get closer, we might give ourselves more time. Let's see, what's our temperature in our pot now? So we're measuring the temperature with the thermocouple. Okay, we're up to 41 degrees. You know, where are we headed? We're headed to 100. Now, let me get over to the screen so I can get a close look at the screen to see what you're looking at. Yes, one thing I'd like to point out is that, do you see some tiny little bubbles? You see some tiny little bubbles that are creating down at the bottom surface of our pot. Okay, that's not boiling yet. Okay, that's not yet boiling. I've got to change my thermometer here. It wants to turn off every now and again. Okay, so whoops. Just excuse me while I'm resetting here. It doesn't like to stay on its own. Okay, here we go. So now we're up to 55 degrees C. I can make this guy stand up better. Yeah, okay. Where was I? The tiny little bubbles in the teapot. Okay. What's happening here is the temperature of the water is getting higher and higher, and dissolved oxygen in the water is coming out of the mixture. So hot water cannot hold as much dissolved oxygen as cold water can. And so right now, we're at 60 degrees F, and dissolved oxygen is coming out. And so that's one of the things that my mom explained to me when I was a little child. So that is the idea of dissolved oxygen And she described to me that's how fish can live in the water. And she illustrated that by these tiny little bubbles. All right, so so we're continuing to watch things going here. We're monitoring our temperature. We're up to 67 degrees C. So right here, right now, it's sort of like we're sitting here watching water boil. So I wish I could give you something more exciting. Can't really make any figures with my hand to entertain you. But one thing, but again, you can be watching how these bubbles are forming and oxygen is coming out of the water. Now, as we get closer and closer to the boiling point, you're going to see the frequency of the little bubbles is really starting to decrease. Now, I can see that with my eyes because my eyes are pretty close to the pot here, that the frequency of the little bubbles is starting to decrease. Okay? And the other thing is, I'm starting to see some movement. You might be able to see on your screen that you can see some convective movement of the water. So what we're looking at, density variabilities in the water. So I think you're starting to see it, and we're getting, that's an indication that we're getting closer and closer to the boiling point. My timer has been going for 4 minutes. I see on the kitchen timer, we're at 6 minutes. We started at 10, so we've been adding heat at a certain rate, so many joules per second or kilowatts, okay, for, well, a little over 4 minutes. Now, I can start to see the beginning of boiling over on this side of the pot. I can start to see what does look like some steam bubbles are beginning to form. But so we're getting closer and closer to the boiling point, and we see that our temperature is 90. Okay, so we're 90, we're getting closer to boiling. Okay. I hope that my thermometer, my thermocouple can hang in there, and if it beeps at me again, I'll have to go back and turn it back on because it'll turn itself off. So remember, we looked up for 100 kPa, we looked up the boiling point temperature, and we saw that it was 99 and change, or right around 100. Oh, and now, okay, now you can visually see the boiling. We are boiling water now, so it's been, okay. I can hear the whistling tea kettle. So at this point, it's very easy to see the boiling. There are various nucleation sites at the bottom surface of the tea kettle. That's how you see these bubbles. To me, it's very cool. So the air, at this point, the air has been excluded from the visible part of the tea kettle. So what you're seeing here, this is a visual look at basically saturated liquid and saturated vapor. And can you hear the whistling of the tea kettle? I can hear it. It's possible that Zoom is filtering out that noise, but I can hear the whistling of the steam leaving the top of the tea kettle. And oh, and it's hot. When I put I've got my hand up here. That's hot. That is really hot. So okay, and where are we on our temperature? Wow, look at this. Amazingly, so we're right at 99, 99, 98, 99 with some variability. We're right there at the boiling point that we looked up in the steam table. So for me, it's just very interesting that this stuff really works. Now, let me grab some notes. I made some notes because we want to let this boiling continue. Because folks that have not been in thermo, they might think, well, if I continue this boiling water, if I continue to add heat down here, if I continue to add heat, common sense tells me that the water would get hotter and hotter and hotter and hotter. But we're observing that the water temperature is not increasing. Why is that? Well, the reason is that our pressure in the teapot is not building up because of the open system. The pressure in our teapot is still 1 atmosphere. And so we've still got that saturated pressure temperature relationship. And so we could sit here till the cows come home and continue to boil, and the temperature of this boiling water would not change. Okay, so that's an important point to make out of this video. Visually observing that once your water's boiling, your temperature isn't changing. Now, let me turn the heat down. So you think, well, I'm going to turn the heat down some. Can you see me? I'm turning it down. I was on medium high. Okay, and now I'm down below medium. So I'm still adding heat. Do you see that the water is still boiling? And the temperature of the saturated mixture is staying constant. So a very important conclusion out of this video is that once you've got your water boiling on the stove, of course, you're in a hurry to boil water. So that's why we were way up high. Okay. And we're down to, we've been at this for about 9 minutes. I'm going to give myself an additional 5 minutes. So hang on here. Okay, I've reset to 5 minutes, and then we'll call it a day. So the point I want to make is once you're up to the boiling point, you can reduce your heat input, which costs you money, just to maintain the boiling, and you're maintaining a constant temperature. So that's important both in cooking on the stove and in industry. Okay. And so recognize that the rate of heat addition has no effect on the temperature of the saturated mixture. All that happens is you're simply boiling water off faster and faster the more heat rate you put in. So I'm going to go back up higher, and I'm hoping that you're going to be able to hear more steam escaping from the pot. Okay, temperature staying the same. And at least in my world, I can hear a higher pitched whistle, which means we're simply boiling water away at a faster rate. Okay, another point to make. Here I've got pasta. So you know that on the stove, we like to make pasta, right? And so a lot of folks think the purpose of cooking pasta, okay, is you put it in boiling water, and there's a certain amount of time it takes to cook pasta fully. So it does not matter what, as long as you keep your water boiling, the pasta will be cooked within a certain amount of cooking time, no matter how much heat you're adding, because the pasta is cooking in a constant temperature boiling bath. And so that's an important point to make. I've encountered a number of folks in various social occasions where we're cooking in the kitchen, and folks who have not taken thermo, they think they can cook their pasta faster by increasing the heat. And that's not true at all. So it takes a certain amount of time to cook your pasta, no matter how much heat you're adding to the boiling water, because you're cooking at a constant temperature. Okay, so that is very cool. I see that we've got 2 minutes left, but I hope that you get the idea. Notice how we've been at a constant temperature for a good long time. All right. Now, so I'm going to go back to the PowerPoint. Let me X out of my timer here so we don't get an alarm. Let's see. I've got to figure out what button to push. Here we go. Okay. The button is pushed. I'm going to go back to share screen, and we're going to recap. Okay, we talked about the system modeling. You see now, okay, so here's a static shot of what you're seeing. Okay, here I am. There's me. Okay, and so you're seeing an open system. You're visually seeing an open system on the camera because steam is escaping from the top of the kettle. Fun facts. So let's mention some fun facts. The boiling point temperature is fully defined by the surroundings pressure. Okay, that's one of the reasons for this video. There's two basic categories. Sensible heating, that's simply raising the temperature of the tap water up to the boiling point. And then what we call latent heating. That's what we're doing now. We're adding heat simply to boil water. That's called latent heating. We're adding heat, we're adding energy to the H2O in order to transform the saturated liquid into saturated vapor. Okay. Next fun fact, the boiling water temperature cannot go above the boiling point until all the saturated liquid is boiled away. We are not going to stay here to do that. And can you imagine what might happen if I boil the water, all the saturated liquid water away, and all I have is saturated vapor? If I were to do that and continue to add heat, at that point, the steam in here would become superheated vapor. And at that point is when we would be raising the temperature of the steam. Okay. Also, I mentioned here the throttling back. You can throttle back the heat setting just to maintain the boiling, and you still are at the same temperature. So if you're energized to repeat that at home, remember that steam can be heated beyond the boiling point, but it's very dangerous because you don't want to have a tea kettle or a pot or anything on the stove that you're heating without having liquid in the bottom of the pot. That's very dangerous, and for risking busting your tea kettle or even melting or singeing a steel fry pan or pot. I've added a slide where you have to imagine putting a piston and cylinder on your stove instead of this open system. In other words, a lid or a piston would be sitting on top of the water, and as you heat the water, you would see what happens to the volume of the closed system. And so once you get to the boiling point, you're going to be making saturated vapor, and the volume skyrockets on you. And so this is just a visual example of what would happen on the stove if you had a piston and cylinder sitting up on the stove. Okay, so finally, we're near the end. Okay, we've got the recap is that our objective was to take tap water, get it up to the boiling point. That's sensible heating. Once we got to the boiling point, we boiled the water, and we had in an open system, and that's called latent heating. And you've observed one of the big takeaways from the video is you can I want you to think about visualizing saturated liquid and saturated vapor. So you can see what a saturated mixture is all about. Saturated liquid, saturated vapor. Okay. And that, I just singed my pointer. Yikes. And so that pretty much covers it. I hope you enjoyed the video. I hope you liked the demo, and hope to see you again on another video soon.